All right, so we're going to solve this integral equation using the numerical quadrature. And in this particular example, I'm going to use a Simpson's one-third rule. And then you can actually apply, the other approaches, or you can just use the other approaches to solve this same question, okay? So the first things you have to put down, always write things out neatly. You're going to need to know what your kernel is, all right? So if that is that, you need to write your Kij, which is going to be your K of Xitj. So that's going to be Xitj. And then your f of x, which is x squared. In the case of xi's, your f of xi is going to be xi squared. And then your yi's are going to be y of xi. And then your yj's are going to be y of xj. Okay. Now, there's a reason why we're using I's and J's, right? So you're going to see that in the course of, you're going to see that as I'm solving this example, okay? So now we are using the Simpson's one-third rule, which means that we can only use segments or which are multiples of 2. So in this case, we're going to use the basic one, which is n equals 2. And you don't really have to use 4 segments. It's going to be a bit tough for you to solve. If you use 4 segments, you're going to have 5 nodes, and then you'll have to solve a system of 5 equations, which is going to be hectic, right? So it's always advisable to use n to be 2 when you're using the Simpson's one-third rule. And if you want to use the Simpson's 3/8 rule, you can use 3, because we want multiples of 3 segments. So just use 3. Don't stress yourself, okay? And then if you want to use a trapezoidal rule, it is also advisable to use at least, let's say, 2 nodes, okay? Use 2 nodes, and then that's going to be 2 segments, and that's going to be perfect, okay? So yeah, the first thing you have to do in this case, you're using n is equal to 2. Your step size is going to be, b minus a in this case, which is 2 minus 1. 1 minus 0 divided by 2, and that gives you 1/2, okay? And then you always have to write your nodes out clearly, okay? So this is your I. So let me make this one. Ij being equal to 0, Ij equals 1, Ij equals 2, right? So those are going to be the nodes, right? If you remember, if you divide this one into like 2, you're going to have x0, x1, x2, right? So these are your i's, right? Yeah. And then the same thing happens for t. So yeah. So for the xi's, we're going to have 0 first. And then 0 plus 1/2, that's going to be 1/2. 1/2 plus 1/2, that's going to be 1. You're going to do the same thing for tj's. They are always equal, okay? So your nodes are always going to be like that. So now that you have your node, okay, you want to write out the general solution to this integral equation, right? So if you remember correctly, we approximate the IE by, okay. So now why are we using approximation? It is because of the integral. It's because of this integral, right? So what we're going to do is to replace that integral with a summation, okay? So now we're going to have y of x being equal to, that is x squared. Now minus, okay, so there's going to be a summation j equals 0. Now you see that we had ij equals 0 up to 2, right? So that's going to be up to 2. And then it is only the t's that are changing. The subscripts of the t's will be the ones changing, because you can see that this integral is with respect to t, okay, not with respect to x. That is why I have my x. That's why I have my x untouched. Okay, yes. So we are not worried about our xi's right now. We are only worried about our TJs if you are writing out the general solution, okay? So keep that in mind. So now this is going to be equal to some alpha j, right? K of x tj, which I already know, so let me just put that in here. k of xj is actually k of xt is actually xt. So this is going to be multiplied by x, and then tj because it's k of tj, right? And then I'm going to multiply this by u of tj, and then that is going to be multiplied by delta t. Mind you, your delta t in the Simpson's 1/3 rule is going to be h over 3. Keep that in mind. So in this case, it's going to be 1 over 2 divided by 3, which is 1 divided by 6, okay? So we can further simplify this, and this is going to be f of x, y of x being equal to x squared. Now this is just a constant, so I can pull that out. So minus delta t summation j starting from 0. Let me not use summation again. Let me just simplify it, okay? So you're going to open a big bracket, and then you know that the alphas at the endpoints are always 1, if you remember correctly. So it means your a0 is going to be 1, okay? Then that is multiplied by x, right? Multiplied by x, and then multiplied by tj. T0 is 0 from here. So you're going to plug that in here. That's going to be 0, and then u of t0, which is 0, then plus, remember I have pulled this outside here, remember this is already pulled out here, so I'm not going to put that here again, remember. So plus, now the next term, since we are using the Simpson's 1/3 rule, remember that the formula is always going to be, your alpha naught. The formula is going to be f of x naught plus 4 summation I when it is odd of f of x I plus 2 summation I when it's even of f of x I plus, f of xn, right? So with the functional values with odd indices are going to be multiplied by 4. So it means that this is going to be, j is actually 1, which is actually odd, right? So we are going to pre-multiply that by 4, right? So your a1 here is 4. Keep that in mind. So 4x, and then tj is 1 over 2. Okay, and then that's going to be u of 1 over 2. Then plus, we have only one more node, and since that is an endpoint, the coefficient is just going to be 1. Okay, and then we're going to multiply this by x, and t2 is just 1, and u of t2, which is just 1. Oh, these are supposed to be y's, sorry. All these are y's, okay? So that's what we have. So now I want to simplify this, and that's going to give us our general integral, the general solution to the integral equation. So this is going to be y of x being equal to x squared minus your delta t. We know delta t to be 1 over 6. So that's going to be 1 over 6. You're going to open your parenthesis. That's going to go to 0 plus 2x y 1 over 2 plus x y of 1. Okay, so we can further simplify this, and this is going to be y of x being equal to x squared minus 1 over 6 multiplying, let me just simplify this. There's going to be I'm multiplying through by the 1 over 6, and that's going to be x over 3 y 1 over 2 plus x over 6 y of 1. Okay, and this is the general solution. So I'm going to call this equation 1, and that, always keep in mind, this is a general solution to, I'm not necessarily general, but the solution to the IE. Okay, so all we are going to look for is your y1 over 2 and y1, and once you're able to get that, you're going to plug them back into this to find the solution to the equation. Okay, all right, so now let's move on. Now that we are done with our TJs, we are going to go into our XIs, all right? So now we're going to have y of x0. And what is x0? x0 is 0. So this is going to be y of 0, which is going to be equal to, you're going to replace all x's with 0 here. That's going to be 0 minus 0 plus 0, which is 0. So y of 0 is actually 0, okay? Cool. And then we're going to do y of x1, which is going to be y of x1 is 1 over 2. I'm going to have 1 over 2 all squared minus 1 over 2 divided by 3. That's going to be 1 over 6. Y of 1 over 2 plus 1 over 2 divided by 6. That's going to be 1 over 12. And then y of 1. Okay. All right. Oh, I think this is supposed to be a negative. My bad. Sorry. So this over here is supposed to be negative. Thank you. All right. So you can simplify this, and then you're gonna have y. So you can group the like terms over here. So you can group the like terms over here, and you're gonna have y of 1 over 2 plus 1 over 6, y of 1 over 2 plus 1 over 12, y of 1, and that should be equal to 1 over 4. Okay, so when you simplify this, I think you're going to get 7 over 6, y of 1 over 2 plus 1 over 12, y of 1 being equal to 4. Okay, 1 over 4, my bad. So you can still further simplify this, or you can just leave this as your next equation. So I always would like you to simplify this. We're going to multiply it through by 12. And when you multiply it through by 12, that's going to be 14 y1 over 2 plus y of 1. And that is should be equal to 3. And I'm going to call this my equation 2. Okay? Cool? Cool. We're going to do the same thing for y of x2. And what is x2? x2 is 1. So that's going to be equal to y of 1. That's going to be 1 squared minus, where is the original formula from it? Always you are doing your substitution into your solution, which is equation 1. That's going to be 1 over 3 times y, 1 over 2 minus 1 over 6 y of 1. Okay, so you're going to try and then simplify this as well, and this is going to be 1 over 3 y 1 over 2 plus y of 1 plus 1 over 6 y of 1, and that should be equal to 1. And then we can further simplify this to give us this is going to be 1 over 3 y of 1 over 2 plus 7 over 6 y of 1, and that should be equal to 1. Further simplify to get 2y, 1 over 2 plus 7y of 1, and that should be equal to 6. And this is going to be my third equation. Okay, so now we can solve equation 2 and equation 3, and that is going to give us the solutions. Let's go. Okay, so when I solve this, I'm getting y of 1 over 2 to be equal to 5 over 32. And I'm getting y of 1 to also be 13 over 16. Okay. So now that I have my y's, actually my y0 is 0. My y1 over 2 is 5 over 32. And y1 is 13 over 16. I'm going to plug them all back into equation 1. Okay. So plug in y1 over 2, or plug in the solutions into 1, right? What are we going to get? We are going to plug them back into this one over here. We're going to have y of x being equal to x squared minus x over 3 multiplying x over 3 y 1/2, that is 5 over 32, and that should be plus, where is it, minus x over 6, and y1 is 13 over 16. All right, so we can further simplify this, and this is going to be y of x being equal to x squared minus 5x over 96 minus 13x over 96. Okay, so we are going to have yx is x squared minus 18x over 96, which simplifies to x squared minus 3 over 16. And this is the approximate solution to the integral equation, okay, using the Simpson's one-third rule, okay. So, for instance, if you're supposed to use a trapezium rule or the trapezoidal rule, what will happen is that the only things that will change will be your delta t, right? And then your number of segments will also have to be multiples of one. It could be anything. It could be three. It could be two. It's up to you to decide. Okay. But your delta t would be h over 2 if you're using the trapezoidal rule. If you want to use the Simpson's one-third 3/8 rule, this is going to be 3 over 8h. Okay. And that also works for that. And if you are using the Simpsons, if you're using the trapezoidal rule and then you're using just two segments, you're still going to have these nodes as your, this table as your table of nodes, and then you don't really have to worry about that unless maybe you want to use three segments. Then you're going to have an additional maybe node, and the only another thing that's going to change is the coefficient here, right? So if you're trying to use the trapezoidal rule, this here would have been 2, okay? Because everything in between your x naught and xn in the trapezoidal rule is just going to be multiplied by 2, okay? Yeah, if you want to use the Simpson's 3/8, that's where, it's a bit, there's going to be a bit of confusion. Because with that, you're going to need a minimum of 3 segments, and then you need multiples of 3 segments. And so, at I or j equals 1, right? That's where you have x1 or, t1, sorry. You're going to pre-multiply that by 3, okay? And then where you're going to have t2, here you're going to pre-multiply by 3 as well. And then, the endpoints are, the functional values at the endpoints will always be pre-multiplied by 1 as well. So that's the only difference, if you want to use other techniques, all right? But yeah, this is how you solve an integral equation using any of the numerical quadrature approaches, okay? So you can be given an example where your kernel is about like e to the x sine t, right? Don't be scared. Don't be scared. This is just kij is e to the xi sine tj. Okay. So all you're doing is you're replacing all the x's with xi's and then all the t's with tj's. Okay. So there is nothing. So you don't really have to worry about the kind of kernel you get. Okay. The only thing that may happen is that you can be having your limits of integration to be some kind of pi over 2 or something. But it's just the same thing, right? Your h is still going to be b minus a over, is it 2 or 3 or whatever you want to do, pi over 2 minus 0 divided by 2, right? And then you're going to use the same formula, delta t being equal to whatever you want to use that for, okay? If it is Simpson's 3/8, it's going to be 3 over 8h, and in that order, okay? And the one thing you have to be cautious about is if you're using certain calculators, you'll have to switch the mode to radians, okay? Yeah, you have to switch it to radians if you have angles in there, okay? Yeah, so make sure you switch that to radians before you start plugging in your pi, else you are going to make mistakes in your final answer, okay? So always make sure to change the mode of your calculator to radians, and then you should be fine in solving this, okay? So all the best. Bye-bye.